So Earth traps only 2 billion part of the heat. Earth traps only 2 billion the part of the total heat released by the sun, which is equal to 1.94 calories square. Then 1.4 is also created to okay, called the two Lagrange point. Even the insulation trap is not uniformly received. So even the insulation that is trapped is not uniformly received on the whole earth of the surface, the reason being the atmosphere. The Some regions has more cloudiness than the other regions. For example, the tropical and the marine type of climate will have more cloudiness than the other regions. Okay. So, so what are the factors affecting the insulation? The first is the revolution of the Earth. Revolution of the Earth has mainly two parts: the perihelion and the aphelion. The perihelion is the month or the time period when the Earth is closer to the Sun. That is during the month of January, when the Earth is closer to the Sun, and aphelion, like now in the month of July, when the Earth moves farther away from the Sun, because we are moving towards winter season, and in perihelion we are moving towards summer season, so we are going closer towards the Sun. And then the comes the perihelion. Aphelion done effect is also uh, high high Melik is. So where are you from? Yeah. So perihelion effect is also concealed by atmospheric condition and land and sea condition. So of course we know that the water has a moderating effect on the climate, and the land gets hot and cooled, too fast. So that's why in inner regions where there are no oceans, or there is a lack of humidity, we see extreme winter and summer season, mainly in the interior part of the India. Hi, Achu. Hi. Hello, everyone. The rotation and revolution on a tilted axis goes on to vary the insulation, of course. So there is also another factors that impact the impact the effect of the solar insulation of the Earth. The first is aphelion and perihelion. So as in perihelion, we have already described it. So rotation of the Earth, the rotation revolution on a tilted axis goes on to vary to insulation. Because of the revolution on the tilted axis, the distance traveled between the insulation also varies. More the distance traveled in the atmosphere, more the absorption, less amount of receive in the okay. So there is more scattering and diffusion. The slope and another factor is the slope and aspect. Okay. So if the sun rays is perpendicular to the earth, still the slope may not be perpendicular. The slope might itself be slanting. The more it will be scattered, the less heat will be absorbed. So it also the heat insulation, the solar insulation also depends on the slope of the surface. So the higher the slantiness of the slope, more will be the scattering of the light, and less heat will be reaching the region. Transparency of the atmosphere. In normal rainfall area, the atmosphere is more clear. If it is dry, the atmosphere will have dust particles. So this dust particles will also prevent the heat and the solar insulation from reaching to the surface of the earth. The atmosphere will have dust particles. Insulation will be less. So slight rain or moderate rain, the atmosphere is almost clear, so we see higher insulation in that type of regions. Now very heavy rain, very cloudiness, again it will prevent the insulation from reaching the surface of the earth. and that's how the solar insolation will vary from region to region and from atmosphere to atmosphere and different weather conditions and climatic zones. Insulation received at different latitudes. So it also depends on the latitudes, as we already know. Equatorial region will receive less insulation due to higher cloudiness in that area, due to presence of the oceans and the seas and the humid conditions, increasing evaporation in that region. And however, if we look at the temperate regions and the polar regions, we see more insulation will be reaching to the surface. However, if we look at the polar region, we will see that the tilt of the sun is away from the polar region, and that's why the polar region will receive less insulation. Now insulation received at different latitudes. So 90-degree north, as we know, 70 meter, and then 22 and a half. Of course, 90-degree, that is the polar regions area, will receive 70 watts. Of course, it will receive less insulation because of the inclination of the earth towards the sun varies. And in 23 and half degree north, that is the tropical regions primarily, it will receive 320 watts of solar insulation. So maximum over the subtropical desert, relatively less. Yes, so you can say it's maximum over the subtropical deserts, relatively in relation to the subtropical desert, it will be less on the equator because of cloudiness of the region. Tropics are less cloudy, hence more insulation. Again, equator will be more cloudy, hence less insulation. At the same latitude, continent get more insulation than the oceans because of the land, as we know, the extremeness that the land has in itself, and water has moderating effect, right? It doesn't get cool or heated up very fast, and that's why in Mumbai we don't experience extreme winter and summer season. Process involved in the heating of the atmosphere. What is the process involved in the heating of the atmosphere? So one is a conduction, the direct contact with the heating zone. Convection, transfer of the heat by a medium, and advection, same transfer of the heat horizontally, but in the same medium, but the transfer of the heat takes place horizontally. So conduction, air is air in contact with ground getting heated. Yeah. Convection, again air becomes hot in contact with the ground, rises up, giving heat to the nearby surrounding areas vertically. That is known as convection. So I think in one process, or in one type of phenomena, every process takes place, like conduction also, convection also, advection also. So conduction is a direct contact heating wherein air is in the ground and gets heated up due to coming in contact with the ground. Convection, air becomes hot due to heatness, it rises up, and vertically it keeps on distributing heat towards the surrounding. And advection is also rising up, but distributing the heat in a more horizontal way rather than the vertical way. Radiation. So without any medium, heat is transferred. Heat coming from the sun to earth, radiation. So different types of radiation we have done. What are the different types of radiation that is received by the earth? The first is the ultraviolet radiation, the visible light, and the infrared rays. The heating of atmosphere vertically and horizontally. So how does the heating of atmosphere takes place vertically and horizontally, and how is the heat distributed on the surface of the earth, which is also known as the heat budget? How the heat is balanced, in the atmosphere, you can say on earth. How is it balanced? We look at that thing. So this I have to rate. effects of perihelion, perihelion rotation, inclination, cloudiness, equatorial, perihelion, sloping, slanting, okay, slope and slope of the rotation, movement, transference, of course, done. Conduction, insulation, disabled. Okay, now we have also seen conduction, convection, advection. Conduction, wherein certain subject matter comes in direct contact of the head, air coming direct contact of the head in the ground. Convection, and then we have seen already advection. Radiation, limiting the sun's energy, the sun's insolation reaching to the earth. That's why we have seen UV, visible light also, I think so, and infrared radiation also. Yeah, done. So now we will be looking at the concept of heat budget, how heat is distributed on different parts of the earth. Isotone, okay. Radiation. How heat is distributed in different parts of the earth.
Hello and welcome to Byju's Exam Prep. Welcome, another session in our knowledge series where we shall be talking about budget. You think about a kind of a balance between things which are incoming and things which are going out. So, budget is something that you would have generally used in the term of the economic balance under general circumstances to your mind. Basic emitted from the sun, budget. So in this session, we shall be talking about more what this term actually means, what do we mean by heat budget, and what are the various different nuances regarding the incoming solar radiation, the outgoing terrestrial radiation. How is it that the surface of the planet maintains that energy balance? We shall also be taking a look at what are the various different factors which can oftentimes lead to slight disturbance in the heat budget here and there, and those are the factors which we refer to as climatic forces. So without further ado, let us begin and let us understand the meaning of the term heat budget. Now here you have to understand that there is an equilibrium between the terrestrial radiation as well as the amount of solar insolation. Now, the energy radiation which is released, which is emitted from the sun, that energy is in the form of short wave radiation. And why is that? That is because sun as an object is very hot and has got a very high amount of energy. So as a result of that, when we talk about solar insolation in general, solar insolation is always carried out in the form of short wave radiation. These short wave radiations, they are very high in terms of energy level. Okay, so energy levels in this is very, very high. Then we also have what we refer to as the outgoing terrestrial radiation. Now, how is it that this terrestrial radiation is achieved? So just like any other object, after a prolonged day of heating, the surface of the planet also starts heating up. As the surface of the planet attains a certain amount of temperature, it starts acting as a hot object on its own. And any hot object will release energy in the form of waves, in the form of radiation. And because we are talking about the planet losing that heat, that is why it is referred to as terrestrial radiation. The terrestrial
Hi,
radiation
Rishabh.
which is released from the surface of the planet, that is always in the form of long waves. That is, it is low on energy level. The energy level here is comparatively low. Now, why is that? Why is it that the incoming solar radiation has got a short wave and has got a high energy level, whereas the outgoing radiation has got a long wave, and significantly, when we talk about it, it has got a low energy level? That can be ascribed to the fact that when we talk about the planet in itself emitting radiation, the planet is much cooler as compared to the sun. So obviously the amount
this
of
globe
energy
has
released
got a
will
hole.
always be much lesser as compared to the sun as well. Now this balance between the incoming solar radiation and the outgoing terrestrial radiation, that needs to be maintained, and that is very, very essential. Why is it essential? Because imagine a circumstance whereby the planet receives more amount of solar insolation and releases less amount of terrestrial radiation. In that case, what do we observe? In that case, over a period of time, you will observe that there is a surplus of heat, and the planet will start getting heated up quite consistently and quite at a rapid pace. The converse of it is also true. For example, let's suppose the incoming solar radiation is less and the amount of heat lost by the surface is significantly higher. That would lead to gradual cooling of the surface and the planet which will become much colder as a circumstance. Now, we know that the planet has maintained its temperature largely. There has not been a much deviation, a much change in temperature for that matter when we consider the surface of the planet. And that is because there is a kind of a maintenance of the energy balance, this energy budget. So when we talk about the heat budget, overall, we consider it in two. Because imagine a circumstance whereby the planet receives more amount of solar insolation and releases less amount of terrestrial radiation. In that case, if and has got a high energy level, whereas the outgoing radiation has got a long wave, and significantly, when we talk about it, it has got a low energy level. That can be ascribed to the fact that when we talk about the planet in itself emitting radiation, the planet is much cooler as compared to the sun. So obviously the amount of energy released will always be much lesser as compared to the sun as well. Now this balance between the incoming solar radiation and the outgoing terrestrial radiation, that needs to be maintained, and that is very, very essential. Why is it essential? Because imagine a circumstance whereby the planet receives more amount of solar insolation and releases less amount of terrestrial radiation. In that case, what do we observe? In that case, over a period of time, you will observe that there is a surplus of heat, and the planet will start getting heated up quite consistently and quite at a rapid pace. The converse of it is also true. For example, let's suppose the incoming solar radiation is less and the amount of heat lost by the surface is significantly higher. That would lead to gradual cooling of the surface and the planet which will become much colder as a circumstance. Now, we know that the planet has maintained its temperature largely. There has not been a much deviation, a much change in temperature for that matter when we consider the surface of the planet. And that is because there is a kind of a maintenance of the energy balance, this energy budget. So when we talk about the heat budget, overall, we consider it in two components. One component will be that of the solar insolation, the other component will be that of the terrestrial radiation. And that is where we try to establish the balance between them. Here you have to understand that with the help of satellite data, satellite information, and also with the help of various different sounding rockets, etc., we have now got a detailed mapping regarding the amount of solar insolation received, absorbed, and reflected from the various different surfaces. That is how we are able to establish the circumstances in which this balance has been maintained. So, when we talk about the incoming solar radiation, and when we take that as an example, here let me elaborate what do we mean by that. So here let us suppose that the incoming solar radiation or the incoming short wave solar radiation, so to say, let us suppose the total amount of it which falls on the top of atmosphere is taken to be 100 units, or simply put 100%, let us say. Now those 100 units of solar insolation which has received on the atmosphere, the top of the atmosphere, not all of it will fall on the surface. Some part of it will be distributed, dispersed within the atmosphere itself. Some part of it will be reflected back into the space from the atmosphere. Some part of it might be reflected back from the surface of the earth into the space. So there we get an idea that some amount of the solar radiation, not 100% exactly, but some amount of solar radiation or solar insolation is actually absorbed by the surface. And that is the unit, that is the quantum that we have to take note of. So here, let's say we take the total solar radiation or the total solar insolation to be around 100%. Out of that solar insolation, around 27 units are reflected upon hitting the cloud surface itself. Because if you take a look at the clouds in general, the clouds, while from the ground surface the clouds might appear to be very dark, blackish, grayish, etc. But whenever you take a picture of the clouds from top, they will always appear to be very bright and whitish in color. So these clouds, they re-reflect significant amount of this solar radiation. And as you can see, around 27 units are directly reflected back because of these clouds. Then, if you observe, then some amount of this solar insolation is absorbed by the atmosphere itself. Now we know that the atmosphere is composed of various different constituents. What are the various constituents of the atmosphere? You have the presence of gases, we do have the presence of water vapor, and we also come across the presence of dust particles. So together, all these three, they end up absorbing significant amount of this solar insolation. And that is also what leads to some amount of heating. For example, if you consider the regions of stratosphere, there we have the layer of ozone. We have what we refer to as ozonosphere. That ozonosphere in itself will end up absorbing some amount of ultraviolet rays and some amount of solar insolation in general, which leads to the heating of the stratosphere. So here around 14 units are absorbed in the atmosphere itself. None of these units, that is 27 which is reflected by the clouds, 14 which is absorbed by the atmosphere, none of these are utilized to heat up the surface. Then if you observe, some amount of these solar rays, they are scattered and distributed with the help of what? With the help of dust particles and other constituents of atmosphere. Thereby there is a scattering of light. That scattering of light not only gives us diffused light during night time and allows us to see even during pitch darkness, but also that works in the sense of trapping of heat. That is why heat is significantly greater closest to the surface. But even while that solar insolation is being scattered, some amount of that amount of insolation is radiated back into the space from the atmosphere itself. So you will observe around 6 units are radiated back into the space itself. Now these 6 units, that is what gives that brightish appearance to the atmosphere when you observe it from the outer space. When you observe the atmosphere from outer space.
So I'm not in any class, I'm doing my master's. So Slasher Box, if you are new to my channel, you can just check my channel. If you like the content, then you can subscribe to channel.
It will always give you a kind of a brightish hue, kind of something like that of a halo, not exactly a halo, but something like that. A brightish hue is what gives us the appearance of that, and that is because of these 6 units which are scattered into the space. Now, after that, around 17 units, they do fall upon the surface, and these 17 units, they will heat up the surface. Now, the solar insolation will also reach the surface in areas where you don't have significant amount of cloud cover, or on average, you can say that around 34 units will reach up the Earth's surface directly without much of an interference. Even from hitting the Earth's surface, you will have 2 units of solar insolation which shall be reflected back into the space. And it is these 2 units which makes the Earth appear like a blue planet when again viewed from the outer space. So this figure around between 2 and 3, that is what is also referred to as the albedo of the
Guys,
planet.
I'm feeling so sleepy.
Now, if you consider this mathematics, you will find that you have, when you consider
I
the
need a
surface
cup
of the
of
Earth,
tea.
you have the absorption of 17 units, right? Which are absorbed after being scattered into the atmosphere. After that, they reach and they hit the Earth's surface. And then you also have an additional 34 units, right? Which reach the surface unhindered and they heat up the surface. So in total, if we have to calculate the amount of solar rays which reach and hit the Earth's surface and which carry on the process of heating of the Earth's surface, you come across a figure which comes out to be 51 units. So out of the 100 units which fell upon the top of the atmosphere, only around 51 units are utilized in heating up of the surface. We are not considering the heating of the atmosphere here, okay? Because atmosphere has got its own independent heat budget. The surface has got its own independent heat budget. Here we are considering the budget of the surface. Now, the energy balance shall be maintained if all those 51 units are re-radiated back in the form of terrestrial radiation. So if we take a look at the long wave terrestrial radiation, that is the energy lost from the surface, we find out that energy is lost from the surface of the planet because of various different activities altogether. So what are those activities? What are those events which leads to the loss of energy? So basically, you have around 23 units which are directly lost from the surface as a result of the surface getting heated up and the surface acting as a hot body in itself. So let's suppose this is the planet. Now, when this gets heated up after a prolonged day of solar insolation, the temperature increases. As the temperature on the surface increases, it in itself starts acting as a hot body, and that is when you will have the long wave terrestrial radiation which is released. This turns out to be around 23 units. Why I am writing here negative is because this is the heat which is lost. Okay, heat gain is generally referred to as in a positive sense, and heat loss is referred to as in a negative sense. Now, we also know that once the surface of the planet gets heated up, the air above it also gets heated up. So some part of that heat is then transmitted into the air parcel immediately above it. As that air parcel gets heated up, that air parcel being lighter and being lesser in density will start rising up. As it ends up rising, what happens? It will transmit that heat from the surface in the upper layers of the atmosphere by a process which we refer to as convection. So convection is a significant measure or is a significant event which also helps the planet or the surface lose that additional amount of heat.
Hi,
This is the
came for
reason
you.
why,
Hi.
if you observe the equatorial areas across the globe, the equatorial regions, they will receive rainfall almost every day in the afternoon, in the evening time, because the heating which has happened throughout, that heating would have led to the convection process. That is how the surface cools, and that convection process forms very dense cumulonimbus clouds, and that leads to further climatic activities. So by this process of convection and various other methods of turbulence in the air mass, the vertical updraft of air, etc., the planet loses close to around -9 units. So you have further loss of 9 units which is experienced from the surface. And then again, by the process of evaporation and condensation in general, when you have evaporation which happens closer to the surface, all those water vapor particles, they get condensed eventually. That is also a methodology of transfer of heat from the surface higher up. So by that process, the planet manages to lose roughly around -19 units. Now here, please don't get confused regarding how do we get these numbers? How do we know it is 23, it is not 22, it is not 21, it is not 24? So as I told you before, this number, this data point is basically derived, is reached at after a host of different climatic experiments which have been conducted for a long period of time. And also nowadays, with the help of satellite data, we are able to map out the different temperature ranges across each and every micro units of the atmosphere, and we get a real-time information of the heat being lost from the surface or the surface being cooled out as a result of it. So that is how we get the number that we are talking about. Now, if you add up all these units by which the planet loses its heat, you will come across something or a number which is remarkable, and that is, if you add it up, you come across again 51 units. So overall, what have we observed is that the solar insolation, the incoming solar insolation,